So the library is being built. We've got our Laplace transform of just 1 or a constant. Remember, if it's a constant, it's just a constant times that. We have our Laplace transform of a t to a power, or a c times t to a power, would just be constant times all of that. Let's move on to the exponential e to the at. Let's transform the function e to the at to be a function of s following the Laplace transform. We always have e to the minus st, thank you Laplace, times the function you're transforming, in this case e to the at. Let's do it. All right, first of all, let me just come over here and say equals because it's all right there. Hey, some algebra. When you multiply, you add those exponents. So we're going to have the integral from 0 to infinity of e to the negative st plus at. And let's just make that look a little bit prettier by factoring out a t. So of e to the, if you factor out a t, we would have negative s plus a, or a minus s. Hope you're all okay with how I did that. Put the t at the end, I like it better, looks nicer. So we just have this integral. So what is the integral of e to the stuff? The integral of e to the stuff is e to that stuff. But the derivative of e to the stuff is e to the stuff. The chain rule would make me take the derivative of the stuff. Remember, a minus s is just a constant. So the derivative of a minus s times t would be a minus s. There's no multiplier of a minus s, and so we must get rid of it. Evaluate that integral from 0 to infinity. So what we have is 1 over a minus s e to the a minus s times t, evaluated from 0 to infinity. Let's see what happens. As t gets really, really, really big, something interesting happens here. A minus s. What if a is bigger than s? What if this is bigger than this? Then a minus s would be greater than 0 if a is bigger than s. And if a minus x is bigger than 0, then a minus s times t just shoots off to infinity as t goes off to infinity. And so in the case where a is greater than s, and therefore a minus s is greater than 0, this integral diverges. Not of help at all. So we're going to make a claim here. And as we do this Laplace transform, we're going to make a stipulation that this only is true if a is less than s. If a is less than s, then subtract a minus s, you're going to get less than 0. If a minus s is less than 0, then a minus s times t, as t goes off to infinity, will approach 0 as t approaches infinity. Because if this is negative, less than 0, negative infinity would make this whole thing go off to 0. So stipulate, as t goes off to infinity, we get 0. Now 0 times 1 over a minus s is still 0. Minus. Plug in a 0. If you plug in a 0 for t, a minus s times 0, e to 0, 1. We just get 1 over a minus s. Yeah, so this integral turns out to just be 1 over a minus s. Ooh, negative. Now, that's fine. You can leave it that way, but it's conventional to do a little bit of algebra on this. Instead of saying negative 1 over a minus s, we can equivalently say 1 over negative a minus s. And if you distribute that minus sign through, we can say 1 over negative a plus s, or s minus a. And so that's a more conventional way to express this Laplace transform without the negative 1 in there. So yes, we're going to say the Laplace transform of e to the at is 1 over s minus a. The library's getting bigger. Next, we'll do a little trigonometry. Have a little sine, a little cosine.